Tony for introduction. So this is Tompin. So I'm from UT San Antonio, and this is a joint work with Huawei US Lab. And first, I would like to thank my students and my collaborators. And also, I would like to thank peer DI reviewers, because this work has been rejected multiple times, 7 times, so to be precise. So, and then finally get accepted by the peer DI review and by peer DI. And also, I owe my special thanks to Emily Berger, who is my former PhD advisor, and then my lab mate Charlie Kosinga. So this was supposed to be my PhD work. So Emily is so generous to let me graduate without waiting for this publication, which appears 4 years later than our expectation. So, okay. So I guess everyone here will agree that the debugging is hard. Or maybe someone don't agree, but at least we should agree the debugging multi-threaded application is hard. Because we have these issues, something like if you have a failure, if you run program again, the failure maybe go away. So how we can solve these kind of issues? So record and replay systems is one kind of systems that can help us. So for record and replay systems, we typically recording some necessary information during original execution, and then when necessary, we have to reproduce that. So that's called record and replay systems. So record and replay systems can be used for different scenarios. So for instance, they can be used for the cyclic debugging. They can be used for the dynamic analysis, security forensics, and fault tolerance. So let's say record and replay systems, they are very important. And that's also the reason why there are tons of research in this field. It's pretty hot and it's pretty traditional. That's another reason that contributes to this fact why it takes a long time to publish. So based on our understanding, there's two kinds of record and replay systems. One is called offline record and replay systems. Another one is called online record and replay systems. So for offline record and replay systems, the replay typically occurs after the decoding. So typically in a different process. For the online record and replay, so typically they will run a decoding and replaying at the same time. They will run concurrently. So however, there are lots of issues of existing record and replay systems. So for instance, one type of systems, they instrument memory accesses in order to avoid some race conditions, reproduce race conditions. So however, it's understandable, the performance overhead will be huge. They can be up to 100x slowdown. And the second type is it's actually pretty hot and more recent research will use the offline assisted analysis. So they only record some part of information, execution information, and trying to use this part of information, trying to infer the correct or possible execution paths. So however, this one will impose low overhead for the recording. However, they will require substantial time of offline analysis. And someone proposed some customized hardware so that to assist this recording. However, as we all know, this customized hardware, they are impractical because there's no such systems. And someone proposed hybrid analysis Chimera. So however, the overhead is still too big. And they may hide some of those concurrent failures. And people from University of Michigan, they proposed this called online record and replay. So mostly including two different type. One is called respec. So they based on speculation. The other one is based on uniparallelism, the double plate. So however, as we can see here, the performance overhead for these systems is still too high. They only test 4 threads. The data is copied from their paper. So over 28% for 4 threads. So it's still too high. And also besides this performance issue and other issues, they still share some of the issues. So for instance, they are not in-situ replayed. So for instance, if you use offline replayed, So for instance, you cannot use that for like online recovery because you have to do a lot of things like offline. And then like online replay. So even if your program may not crash or may not have failures, so you still need to run like both versions like concurrently. You may waste resources unnecessarily. And also, of course, most of them, they are not identically played. So for instance, they didn't handle like memory layouts. They didn't handle, for instance, system states like process ID and that kind of thing. So if like it's not identical, so sometimes it's just difficult to design tools based on that. And then also they cannot like reproduce all failures, so you can refer to our paper for more details. So our like work is called iReplayer. We choose different design goals. So the first one is we are targeting called in-situ replay. So in-situ replay here we indicate like replaying will occur in the same process as original like recording process. And the second one we target is called identical replay. So everything should be exactly the same as the original execution. So if you have a failure on one address, so if you do the re-execution, the failure should be occurred on the same address and caused by the same value, for instance. So this, as what we said, can be helped on the reproduce. And then like we target the code efficient decoding, like the overhead should be low enough in order to be actually used. And also we target like convenience. There's no need for customized hardware. There's no need for like a customized OS, or you don't have to change your code. You don't need to do the decompilation. So let's start with like the overview of the iReplayer first. So iReplayer takes like in-situ and identical replay, and it divides the execution into multiple epochs. So in the beginning of the epoch, so we actually take a snapshot of like memory state or other things we're going to talk about. And then we let the program to run as usual, but with like minimal decoding until like they reach some like irrevocable system calls or some other like resource like criteria. For instance, if I only have like 4 gigabytes memory, I want to limit like the memory used by the decoding to a certain amount. And then at that time, those like threads met these situations will become a coordinated thread. So the coordinated thread, we are trying to stop other threads first. So, and then like we can do something like necessary checking. For instance, if we want to use that for like some tools, for instance, buffer overflow detection, and then we maybe want to like stop the program and then check whether overflow happens or not. If like there's no issues, and then we can let the program to move forward, for instance. So, and then goes to the next epoch. And at the epoch, we will take a snapshot again. So, and then, but if there's some failure, and we will like maybe find out that, and then we can like coordinate different threads to go back to the last checkpoint. So at that point, like everything is fine, and then we can like do the re-execution. In the re-execution, we can actually do some like decoding or necessary decoding or other instrumentations in order to find out, for instance, the root cause of some failures or other like necessary like functionality you can imagine. So, and then like during like the execution, we can perform something like we can collect some information and do some analysis. So that's kind of like use cases for this iReplayer. So the question is how we can achieve this in-situ and identical replay efficiently. Because if the overhead is too high, then will be no use. So, and let's start from like reasons of non-determinism. I guess like most people here already knows that. For instance, when you have non-determinism can come in from like the application itself. We call like internal reason here. So like synchronizations. So which one like grab a log first maybe affect your execution. And the second one is like memory allocations and deallocations. Why like for instance, when you do a like malloc, the malloc may return different value. So that may change your like execution. And also some race memory references. And also like some external reasons like system calls and external inputs. For instance, system calls like get time of the date. If you re-execute the same program again, the same system call will return different value. So I guess that's understandable. And like we briefly like mention how we're going to solve these issues. So for instance, for synchronization order, we propose like something called local ordering, but I guess local ordering already, like someone already like proposed this, but we use a different like data structure in order to reduce overhead. We're going to talk about that. And the memory allocation and deallocation, we actually propose like a customized like a memory allocator in order to reduce like a recording overhead. For instance, we don't have to record every memory allocation and deallocation because that's just too expensive. So we're trying to like use like a customized memory allocator, trying to reduce this like recording overhead. And for the lazy memory references, so I guess like most people here, they are more, that's your concern because you're working on race condition, detection, or other stuff. So we actually like handle that in the replay phase. So we're going to talk about that. So the same idea actually already be applied by this spec, but we actually apply that in a different environment. And also system calls. So we actually like handle system calls, but we adapt to the in-situ setting. So because we use the in-situ setting, sometimes we can actually take advantage of this fact to reduce overhead. So I'm going to talk about like system calls first. So we actually like divided system calls into like different kind of file types, for instance. So the first one, because we are targeted in the in-situ setting. So for instance, like the PID. So if you call or get a PID again, because we are in the same process, we don't have to handle that. So we actually, for these repeatable system calls, we don't have to handle that. That's what we take advantage of this called in-situ setting. So, and then like for some of like system calls, like get time of date. So we will do like the same as existing work. Basically, we will record the results of those like system calls, and we will going to replay that during the execution. And then like there's something like special, for instance, revocable system calls. So for instance, file read writes. So if you are used offline, maybe you have to like record all of those contents on like read and write on file. But because we are doing like in-situ setting, you don't have to do that. So as long as you can, before you read execution, you can recover the pointers, file pointers. So you don't have to do like record the contents of the files, as long as there's no overlap. When there's some overlap, for instance, you use a seek to change the file pointer, we actually treat that as a irrevocable system calls. And also there's something different, it's called deferrable system calls. Like for instance, close. If we close the FD, because we do like in the same process, so if this FD has been used by another, like for instance, open system call, and then there will be trouble. So we have to do that like specially. So we typically say, okay, for those closed system calls, we don't do the close. We like delay the close until next epoch, until we know that there's no need to replay it. So, and also sometimes we are just lazy. We just call those the called irrevocable system calls. So for instance, fork. So you have a new process, although we can do this like recording a fork and then like giving the same value back, but we are lazy. And also like seek, for instance, we're trying to avoid a situation we just mentioned. So we will stop current epoch. And also we also handle the synchronizations differently. So we actually propose this called per-thread list. So to like record those synchronization events and the system calls. So basically, when you have like an event, so we will put this event into per-thread list first. And then like we check, okay, whether this is a synchronization or it's a system call. If it's a synchronization, we will link back to the like different like synchronization. For instance, we have an example like this linked in the top, and in the bottom it's our like structure. So how are we going to use that? For instance, we show these results. We have like thread 2 acquire log 2 first, and thread 1 acquire log 1 first. We basically just add a link there. Although we will save like the address of those logs there into this called per-thread list, and then we will add a link there. So for instance, if like now like the thread 2 release the log 2, and then thread 1 acquire this log, and we will like add a like a link between the first event of thread 2 to the second event of thread 1. Okay, so on and so forth. So we can actually have like this information. So actually, like this data structure is pretty useful for us to reduce the overhead. So for instance, we use like local ordering to guarantee like identically reproduce. And also we're going to use pre-allocated list to avoid like allocation overhead. And there's no need to acquire like additional logs when we do the recording. And also it's worth mentioning, I mean, this like list is very useful when we do like the replay. So because the events are already connected via this called per thread list and per variable list. So for instance, we can use very simple rule to guarantee identical like reproduce of the synchronizations. So we use a very simple rule, say if an event is at the header of the both per thread list and it's per variable list, and then thread can proceed. Otherwise, they have to wait. We use like additional like per thread like conditional variable and mutex to guarantee this order. Okay. So and then how we can do like identical allocations and deallocations? We observe something, say if like memory allocation and deallocation, they just occur inside each thread. So they will be determined by the program order. So there is no need to, I mean, to do like, for instance, decoding if we do something. So if we can separate like the internal like memory use and application memory use, and if every thread have its local like heap, and we can, because like when every thread have its local heap, we only need to control interaction with outside, like other threads. So we actually like use like heap layer, like, and then we adapt this called per thread like heap. So we control like the allocation and the allocation. So if like every per thread heap, they're trying to acquire like a block from the super heap, so we control that use like a global lock, and this global lock will be guaranteed to be like identically, like or deterministically produced. And also the allocation, if you free an object, this object will be only be free to the current thread, so that they will only affect something like later. So we will not like we will guarantee like a deterministic like reproduce of like allocation and deallocation. And also we handle this in the replay phase. So the idea is we have that data structure we just mentioned. So we keep those events in the per thread list, and then in the execution we keep check whether like the event is expected or not. If it's expected, and we keep going. If it's not, and we replay and then try again. We keep trying in order to until we find a matched schedule. So that's kind of the case how we handle replays. So we actually handle like weights, I mean different kind of weights. This is actually the most challenging part. So you can refer to our paper, how we handle that, like how we cleanly stop and cleanly load back. So, and let's take a look at results. So this is the overhead. So we compare to default and CRAP. CRAP is like 2013, I think, PRDR paper. And we use normalized runtime. So iReplayer like only like impose 3% performance overhead. So while like CRAP will be like impose more than 2 times overhead. So, and then we also do some evaluations like identically execution. So basically like we take a snapshot of the memory image of the original execution and the replay phase. And then we use byte by byte compare, and we identify there's no like difference. So for like this like original execution and reproduce, and we think okay we achieved identically execution, and we also like mention try like how we can reproduce crash like race condition. So actually we have a pretty high probability to reproduce race in one execution. Okay, so this enables a lot of like possibilities like dynamic analysis and then failure diagnosis and failure prevention, and those two will be our future work. But we already did something in our paper, like detecting buffer overflow and use of the free, which is the same as our previous work, double take. So, but we do something like differently. We provide a called interactive debugging tool. So something like, for instance, if you have a program and you crash, and in this one we call crash iReplayer because they link to our library. If it's a crash, and then we can like start a GDB and then attach to that to find out like what's going on. So this is like how we do that. Okay. So, and then we can use like, first to find out which thread has a problem. When we have that, so we can go to that thread. Oh, it's so slow. Okay, sorry. And then we can find out it's crash, like a crash in like 46, for instance. And then we can list the problems there to see like which variable has an issue. So it's a shared pointer actually have an issue. We print that and finds out the value like equals to 0. That's why we crash. So, and then like we want to know like why they will crash. And we install a watch point. We use a watch on this variable. And then like we just keep running the program, and then they will crash first. So after they crash, we can say, okay, whether you want to like do the rollback or not. So we propose like several commands like rollback, continue, or exit. If you want to rollback, we can like push this R button, and then it will roll back. And because we already set the watch points, so every memory access on this variable and then will be cached. Okay, so and then we can find out which place have this like cause the program to crash. Okay, so for instance, we can find out the line 19 actually set this variable to null. That caused the program to crash. Okay, so in conclusion, so we provide like a different kind of like decoder and play system with existing ones. And then like we handle like system calls differently based on this in-situ setting. And also we propose like a new data structure trying to like decode those system calls and like synchronizations and also deploy that during like the execution. And the overhead of our work is very low, only 3%. So I'm going to take more questions on that. Thanks.
Questions?
So in recording on execution, you stop other threads when a thread meets system calls, right? So is it possible that that additional behavior, additional stop, you stopping the other threads
yes.
may, by doing that, maybe you lose some races. Is it possible?
Oh, you mean when you happen to be like do the stop?
Yeah.
I guess it's possible, but we target something, some situation, for instance, if you have a crash. At that time, maybe you doesn't care. You want to find out why your program will crash first, or some other situations. Yeah, yeah, it's possible, but I guess like mostly we didn't find anything. Yeah. Hey.
Another user level question. I wonder what assumptions you have on the code. You can replay, for example, parallel code with exceptions and or maybe loading external binary libraries. Can you handle?
You mean loading
cases?
external like binary?
Yeah. So
Yeah. Yeah, that's a good question. I haven't think about that.
Do you handle synchronization through atomics, or you just deal with that as
Yes,
though?
that's a very good question. Currently, we didn't, but we know that someone already handled that. We just didn't implement that. So I think like Custer already handled that kind of things. But if we do that, we have to like we lose some properties. So we have to do like instrumentation stuff in order to handle that. Yeah.
Any more questions? No more questions. Okay, thank you.
Okay. Thank you. Thank you.